Okay, let us start our meeting today. It's our first time to have some scientific meeting in the science hall place. It was accommodation, some room for conference. Yeah, and our first speaker will be Evgeny Smirnov, who came from Shantou, about combinatorics of Lascoux polynomials.
Thank you very much, and I'd like to thank all the organizers and especially Ivan, who brings everything to motion here, and it's really a great place to be, and I think we'll make this place a real home, as the name suggests. So I'm looking forward to to an amazing weekend full of insights. And okay, so let me start. I'll speak about my paper with my student Ekaterina Presnova from HSC Moscow, and I'll be speaking about combinatorics of Lascoux polynomials. And Ваня, оно не работает ничего. Я могу картинку переключать?
Попробуй.
Вот нифига не могу. Я попробую on-off. Оно просто не добивает, наверное. Где там это самое? Красиво. Как-то... Ничего не работает. А, так. Заработало, погоди. Стой. Или это ты нажал? В конце концов сработало. Что, мне тут стоять? Да. Мне кажется, компьютер передвинуть проще, чем меня. Нет, не проще?
Не проще. Я попробую. Require section here.
Сейчас, там ресивер нам здесь, да, попробуем. Нет, ничего не работает. Oh, you told me. I have broken everything. Нет, не проще.
Давай.
Well, I can.
Ставишь сюда, будешь нажимать. У меня работало.
У меня все работало, да, отлично. Вот у меня здесь у меня тоже работает. Okay, so well, let's start. So what? I understand that's kind of you need to look both sides. Okay, so what are Lascoux polynomials? These are some polynomials with integral coefficients and in n variables, x1, etc., xn, and in there I also have some parameter which I call beta, and this polynomial depends upon two pieces of combinatorial data. These are lambda and w, where lambda is a partition, so weakly decreasing sequence of integers, well, n of them. Well, some of them are allowed to be zero, but zeros are, of course, at the end. And w is a permutation in Sn, and I'll use the standard notation. Si will stand for the simple transposition changing I with I plus 1. So Sn is generated by n minus 1 of these with usual braid relations, so for commutativity, and also and also the braid relation, and the square is equal to the identity. So it doesn't point to the twistry somehow. So anyway, and well, for the length of permutation is the number of inversions, so the number of I and j such that I is less than j, but after applying w, the order flips, right? So w of I is greater than w of j, so the length is something between 0 and choose 2, and the maximal length permutation is just bringing everything to the opposite order, bringing 1, etc., n to n, and minus 1 to, well, etc., 1, right? So here we fixed our notation about the symmetric group, and let me pass to definition of these polynomials. So I'll do this in 2 steps. First, I'll define divided difference operators on the ring of polynomials with integral coefficients without any beta so far. So what is a divided difference operator? This is the following thing. So let me take a polynomial and in, well, n variables, and switch variables number I and I plus 1, and take the difference of these. So I'll get something skew symmetric in I and I plus 1. So this means this skew symmetric thing, well, it will vanish when I is equal to xi is equal to xi plus 1. So it will be divisible by xi minus xi plus 1. And, well, the ratio will be still a polynomial with integral coefficients. So this is a divided difference operator, something, well, say, something similar to partial derivative, you know, it's defined by the same symbol, essentially. So, yeah, but the properties are somewhat different. So, first of all, it's a polynomial, and I divide a skew symmetric thing by a skew symmetric thing. So I get something symmetric in xi and xi plus 1. And so if I, on the other hand, if I apply something from to a polynomial that was already symmetric, this means that well, the numerator will be 0. So it means if I apply the same thing twice, the same di applied twice, well, it will become symmetric on the first step and will vanish in the second step. And as you can check, well, a part of this relation that this thing is nilpotent, the other relations are the same. So they satisfy par commutativity and rate relations. And, well, the degree of f if is dropping by 1. Well, unless f was symmetric. Questions? Okay, so let's well, since there was a question from let me give you an example. So let me apply d1 to x to the power of 5, x2. So I need to take x to the x1 to the 5th, x2 minus x1 x2 to the 5th, and divide this by x1 minus x2, and I'll get some of a geometric progression, right? So something that, well, that probably resembles the character of SL2, and it's the same thing. Okay, so now I need another family of operators. I need to twist them a little bit. These are homogeneous divided difference operators. So, and here is the moment when I introduce beta. And so I define my pi I as divided difference operator di, partial I, applied to f multiplied by xi plus f multiplied by xi plus 1. So you see the degree is bigger now, and then I multiply it by beta. So what is it good for? It's this thing is idempotent. Its square is equal to itself. It satisfies the same relations, and but it is homogeneous. Homogeneous. Well, it were homogeneous if there were no beta, but it really becomes homogeneous if beta is assumed to have degree -1. Okay. So, well, let me look at a pretty similar example. I take x1 this time to the fourth x2, and I get the same, essentially the same polynomial in x1, x2 without any beta, plus beta times a shorter geometric progression of degree 1 larger. So let me draw this as the following picture down in the bottom right corner, that I denote these things without betas by points, and beta times something by edges. So, well, edge is one-dimensional, so b comes in dimension in degree 1 here. And well, the vertices have dimension 0. So so we'll need this picture. So I just want you to well, to memorize it. We'll need it in some 20 minutes. Okay. So now I'm ready to define Lascoux polynomial. Well, as suggested by well-known Arnold's principle, Lascoux polynomials were apparently first defined by Sergei Fomin and Anton Kirillov. Well, we can start with a certain partition, and given a partition, we can consider the monomial given by the same degrees, by the same lambdas, a monomial in x1, etc., xn, with these exponentials weakly decreasing. And to this, well, and so I need one more ingredient. I need a permutation. And I can take my permutation and represent it in a shortest way as a product of simple transpositions. So this is a reduced decomposition of my permutation, and I take the corresponding product of pi's. And I can apply this operator pi w, and you see, due to the relations in the symmetric group, this thing is actually well defined. It does not depend upon the reduced decomposition. So I can apply this pi w to x lambda and get a polynomial in x's and beta, and this will be the homogeneous. This will be a homogeneous polynomial of the same degree as the degree I started with. Well, the sum of all lambdas, and well, you get such a nice family of polynomials. For various lambdas, they form a basis of the ring of polynomials, and the trivial case is where you start with the identity permutation. So your pi is just the identity operator. So you still get a monomial, but an interesting thing happens when you apply W naught, and as you can pretty easily see, what you get will be a symmetric polynomial, because like applying every pi brings it to itself. So, and these polynomials, they are called symmetric Grothendieck polynomials. and they are a non-homogeneous deformation of famous Schur polynomials, and they appeared in the study of K theory, or more precisely, connective K theory of Grassmannians. So beta is this parameter for the connective K theory, and if you assume beta to be -1, you'll get just the regular K theory, and yeah, this was studied by Fomin Kirillov, by Lascoux. Combinatorially, they were studied by Anders Buch, and well, I'll speak about some combinatorial interpretations.
So can you repeat what's omega this permutation? Omega 0 1.
No, not. It's the longest permutation. It's yeah.
And it's hard to prove that it's symmetric.
No. It's well. So in fact, if you so the thing changes if you apply pi, if the length of your permutation is increasing. So you cannot apply any simple transposition to W naught to increase the length. So it will be simple.
No.
Answering questions. No, it's not hard. We have done it. Okay. So and as I said, these polynomials are related to various families of polynomials from.
Sorry, your first polynomials are beta dependent.
Beta dependent, yeah. Yeah. Right now it's sometimes people add like upper index beta, but I don't do that. Gonna be too bulky. So yeah, my Grothendieck polynomials are beta dependent. They are connective K theory. And so I already told you that if you specialize this, if you specialize W to W naught, you get symmetric Grothendieck polynomials. And if you specialize beta to 0, you get something called the key polynomials. And I'll tell you in a minute what they are. And the representation theorists think of them as characters of Demazure modules. And if you do both things, if you specialize beta to 0 and take W equal to W naught, you get just Schur polynomials that appear as characters of irreducible Gelfand modules and as representatives of cohomology classes of Grassmannians. So an interesting thing here is that that Grothendieck polynomials have a geometric interpretation, but I'm not aware of any representation theoretical interpretation. So, and with Lascoux polynomials, it's even worse. You can define them combinatorially, well, in this way, but it's unclear. Well, there should be some geometry behind them and some representation theory, but this kind of still remains a mystery. So what are the key polynomials? These guys have representation theoretic description, and let me give it to you. So I can take an irreducible Gelfand module with defined by the highest weight lambda, and well, here I wrote the picture is supposed to represent the weight diagram of this module, and so the highest weight vector is V plus, and the Borel subgroup positive Borel is acting in the to the right and to the top. So you can take well, this, by the way, this polygon is, well, here it's a hexagon. In n dimensions, it will be an n-1 dimensional permutohedron. So it has, well, if your weight is strictly dominant, it has n factorial, n-1 factorial vertices, and you can, yeah, n factorial vertices. So 3 factorial is 6, right? So you can take one vertex of this polygon, polyhedron, and generate a B submodule by this vector W V plus. So you just take the span of what you can get by applying Borel to this W V plus. So this is called Demazure module, and the key polynomial corresponding to lambda and W is just its character. Well, and of course for the key polynomial for W naught is just Schur polynomial. And what you recover is more or less, well, the definition we had is more or less Wiles character formula. Okay, so now let me speak about some combinatorial formulas for Lascoux polynomials that were, well, in fact, I'll pick about one interpretation of Lascoux polynomial that was known before, but it's a pretty recent object. So I think that, well, these papers were, well, dates that's almost 5 years ago. So let me take a partition and a permutation. So I can apply this this permutation to this partition and permute the entries of my partition, and what I'm gonna get is a weak composition. So now the order matters. So these guys do not necessarily decrease. So some of them are allowed to be there are entries of this type, and well, this will be alpha will be denoted by alpha 1, alpha n. And given such a weak composition, I will form a certain semi-standard Young tableau, which I will denote by key of alpha. Well, they are key polynomials, so there must be a key somewhere. So, and I will define it by the following property, that this semi-standard Young tableau will have alpha I entries equal to I in the columns 1, 2, etc. alpha I. So in every column up to certain one, you have this type of entries. So so this is bijection between such semi-standard tableaus correspond to weak compositions bijectively. And well, here's an example. I take 1, 0, 3, 2, and I should take one entry equal to 1. Well, the purple 1 in the upper left corner. The 0. Well, I need to take 0 2s, so I don't take any 2s at all. And then I have the number 3, so I need to put 3 to columns 1, 2, and 3, right? So the blue one, the dark blue ones, and the light blue one is, well, alpha 4. So I need to put 4 into columns 1 and 2. So, well, easy enough, right? So here's the definition of key, and now I can I will consider the set of all semi-standard Young tableaus of the same shape that are entry-wise, well, here is well, smaller or equal to the key. So, for example, in for 0 to 1, well, the key will be the right-nose Young tableaus. So there are 2 2s and 1 3. So I listed all the Young tableaus with entries not exceeding the entries of the key entry-wise, right? So there are 5 of them, and now, given a tableau, I can take a monomial just by multiplying all the x's with corresponding numbers, the numbers corresponding to the entries of my tableau. So in the first one is 1, 1, 2. So I get x1 squared, x2. The second is 1, 1, 3. So I take 1 squared, x1 squared, x3, and so on and so forth. So the last one will be the one corresponding to the key. So it will be exactly x to the power alpha, right? Okay, so an old theorem, well, the theorem by Lascoux says that what you get is the character of a Demazure module. So this is your key polynomial. Okay, so now you need to modify. So we would like to modify this construction a bit to get Lascoux polynomial. And let's do that. So well, this was known for quite a while for symmetric Grothendieck polynomials, but for Lascoux it's pretty recent. So we consider set valued Young tableau. So we can take the same key, alpha, but now we are allowed to put into boxes our Young tableau not just entries, but sets of these entries. And I would, well, there is an interesting rule that well, your semi-standard tableaus are supposed to weakly increase by rows and strictly increase by columns. So my condition is as follows. So for any two boxes in the same row, I would like every element in the left box to be less than or equal to any element in the right box. So it's funny. This order is not reflexive. If your set is not a singleton, 1, 2 is not less than or equal to 1, 2.
So you mean you use set theoretical tableau?
Set value tableau, yeah.
Okay.
Yeah, and set value tableau with entries not exceeding the corresponding entries of the key. And it turns out, well, here, for example, well, of course, I'll get everything I get in the case of the key polynomial, right? So this corresponds to sets with one element, and I will get something extra. So this extra thing will correspond to actual sets. And my beta will be, could you tell from this picture what is beta equal to? Bart.
I was trying to decipher.
So you see all the tableaus have 4 numbers in there, and the last one has 5. Yeah. So normally you have like 3 boxes. So this is excess, right? So the number of extra entries you put into your tableau. So this is the power of beta. This is this grading, this extra grading you have. So of course sometimes you'll get the same monomial. That's okay. And well, it turns out that what you get is a Lascoux polynomial. Is the Lascoux polynomial corresponding to this alpha. This is a recent result of Tianyi Yu he defended his thesis this year in San Diego, and now he's in Montreal, and well, originally from Guangdong province. So here we are. So here's a combinatorial formula for Lascoux polynomial. But I would like to bring some polytopes into this picture because I like not only combinatorics but also geometry of polyhedra. So and what are nice polytopes? Well, I like Gelfand Zetlin polytope. So let me pass to them. Yeah, well, and there are at least 2 other formulas also by Yu and his collaborators using reverse set value tableaus, Kohnert tableaus, and there are some funny bijections between these situations. And so, but I'll present yet another formula, including involving combinatorics of polytope. So what are Gelfand-Zetlin polytopes? First of all, my remark is that Zetlin is the name Zetlin can be written in at least 3 different ways. So sometimes it's TS, sometimes it's Z. I stick to Z. Some people use C. So let me start again, as usual, with a partition lambda, and let me form the following triangular array: x1, 1, x1, 2, etc., n minus 1 of these, which I put shifting by half of a step under lambdas. Then I take another row, the second row, well, the lambdas will be row 0, then I'll take x's, there will be n minus 1 of them, and this is row 1. Then I shift everything by half of the step again, and this will be n minus 2 of these, and so on. So I get a triangular tableau. There are n choose 2 of x's, of these coordinates. And I interpret my picture as a system of inequalities. A system of inequalities is the following. Whenever I have a triangle, C between A and B in the bottom row, I'm saying that this corresponds to C being between A and B. And, well, my lambdas are fixed, so every coordinate just runs over a certain segment, maybe prescribed by the coordinates on the top. So, well, sometimes this segment will be of length 0. So this is called Gelfand-Zetlin pattern, and if your x's are if these entries are integers, but but I will consider a polytope in R n choose 2, or so not just integer points are important for me. So let me give an example. So this is the only example I can draw. Oh, well, for n equal to 2, this is just a segment. It's not interesting. For n equal to 4, well, I cannot draw a 6-dimensional polytope. So we stay with 3. So you have 3 entries, lambdas A, B, and C. So I reverse, for some reason, I reverse my lambdas. I write them from right to left. But yeah, people write these Gelfand-Zetlin tableaux and the Gelfand-Zetlin patterns in all possible ways. So here's my x is between a. There is a mistake in the first row, of course. Yeah, so x is between a and b. Y is between B and C, and Z is between X and Y. So X and Y give you some sort of rectangle, and Z varies in a fancier way. So what you get is just a union of 2 triangular prisms, or you can think of it as some as a cylinder over a rectangle that you cut by 2 planes meeting on an edge of this cylinder. Well, so you see that this polytope is not simple. You have a vertex with 4 edges and 4 faces, so bad one. So that kind of makes our life more complicated if we try to refer to things like toric geometry, because in toric geometry people like simple polytopes, but that's not the case for us. But that's not bad, not too bad, I would say. Let me say what are faces of Gelfand-Zetlin. Well, a face of a polytope defined by inequalities is usually obtained by bringing some of them into equalities. So, for example, if I take this polytope and I take the red face over there, this corresponds to x equal to b and z equal to y. So I will draw them by diagrams with dots and edges like the one you have on the right. So, but you see that I cannot just put edges in an arbitrary way. They're not independent. If I have some, if I have a pair of edges forming letter V, then this means that the guy upstairs is equal to both of them, and they are equal to each other, right? So the guy upstairs should be equal also to those on the left and the right of him. So having a V gives you another like lambda on top, so you get a full diamond. And say if you impose two relations like upstairs, the bottom guy should be equal to them. So you get a whenever you have two edges meeting, well, going up or going down, you have a full diamond. So, and let me say that I will consider so-called dual Kogan faces that will be especially important for me. These will be faces that are given by equalities going from bottom to the right, not to the left. Like, unfortunately, I cannot point on this screen. Yeah. So like this one, not that one. Okay. So so we just and these are independent, fortunately. So there are no V's, no lambdas. So I just need to take any combination, any collection of facets of these edges and take their intersection. So my polytope is, well, this means that my face contains the like the point, well, the top right point, right? So and whenever you have such a face, you can assign to it a permutation in some combinatorial way. You put simple transpositions on edges, and then you read this thing bottom to top, right to left. So for, say, in this example, you have S3, S2, S3, S1, and this gives you a permutation that I denote by W tilde. And if this word is reduced, then I say that my face is reduced and it corresponds to, and the permutation corresponding to this face is not W tilde, but for some reason I need to multiply it from the left by W naught. So the number of edges corresponds to the so yeah, so if you have, say, one edge, W tilde is a simple transposition, and W of F is has length and just 2 minus 1. Okay, so in particular, the dimension of the face is equal to the length of this permutation. So in this case, well, for W naught has length 4, so if I multiply by W naught, I get S3, S2. So I get a two-dimensional face in the, well, and you can actually see what are the letters, what are the letters you need to read.
So can I ask?
Yeah,
What
sure.
if the word isn't reduced? You just reduce it and then you have.
No. If my word is not reduced, I'm saying that this face is not reduced. And well, in fact, this is a really good question, because you need to take the word that you reduce, but in a smart way. You need to take the Demazure product. You need to take SI squared equal to SI. So you kind of multiply these entries in a lazy way. So if the length decreases, well, you just omit this letter. Okay, so yeah, this really makes sense. So when you pass from when beta enters, right? Okay. So let me first give you the result how to read key polynomials from Gelfand Zetlin polynomial. So the bottom line here is that for each cogn phase, I have a for each reduced cogn phase, I have a permutation.
Can you remind me again, like how you assign SIs to this space?
SIs are SIs are just written here. So S1 on the first one over diagonals.
Okay.
And well, that's
okay. Okay, I see.
Yeah. So, and then you just read the corresponding letters, or you do not read the corresponding letters, depending whether you want to get W tilde or W. Okay. So here we go. So for each reduced phase, you get a permutation. Sometimes you get the same permutation for different phases. So for permutation, you get a collection of phases. And yeah, and that's and one more thing, that our Gelfand Zetlin polytope can be projected into the weight polytope, and that's actually how Gelfand and Zetlin introduced these kind of patterns. They were trying to index some bases in representations of GLN. So you just take sums over rows. And this is a projection into R to the power n minus 1, where your weight polytope lives. So integer points come to integer points, but this is a surjective map into the weight polytope. And so for an integer point, you can form from a point you can form a monomial. Well, in a certain way that that is essentially taking these powers, or maybe taking n minus these powers, or something like that. So depending on the way how you usually write key polynomials. So let me show you where do phases go. So it turns out that, well, so for example, if you take one of the two-dimensional permutation, for this permutation, permutation of length 2, for it you have a collection of two faces, and this is the only case where you have two faces for the same permutation, and this is projected into a trapezoid in the hexagon. So this is the three-dimensional picture has two faces in it, not lying in a plane. But when you project it, well, you get a trapezoid. And the rule how to so for each W, you can take the collection of faces corresponding to this W, and you send it by this projection into something inside the weight polytope. Something will be not, or this will be not a collection of faces, right? So here it's like half of the hexagon. So, but it turns out that if you take the that this thing is actually the character of the corresponding Demazure module. So you remember this picture, right? So for a hexagon, you took like one extremal weight, and you're taking everything you can get from it by the Borel. So essentially, that's what is happening here. So theorem due to Valentina, Kiritchenko, Vladlen, Timorin, and myself is that you need to to get the key polynomial corresponding to lambda and W, you should take the collection of faces with this W in the Gelfand Zetlin polytope GZ lambda, take the integer points and project. So what you get is the key polynomial. What about the last one? So that's the idea here is as follows. So you take integer points and you get some polynomial. And as you probably remember, I was thinking about Lascoux polynomials as something with betas, and I had this picture with edges and vertices. So this picture can be extended to the Gelfand-Zetlin case. So I can construct some special cellular decomposition of my polytope. I can cut it into pieces, into I would say polyhedral pieces, but this is essentially not. There are, strictly speaking, not polyhedra. They can be like they can have a segment with three dots on it, for example. But still, I take a cellular decomposition with integer points being zero-dimensional cells, and essentially these cells look like unit cubes. Well, in the middle of the GZ polytope, but funny things start appearing on the edge. But to each cell of dimension d, I can assign a monomial with beta to the power d. So this generalizes my picture. Well, I say almost each cell because there is some combinatorial condition for some cells. I need to assign 0 to them. I need to omit. Okay, so for this cellular decomposition, the Grothendieck polynomial is obtained as a sum of these monomials with the powers of beta. So if you restrict yourself to zero-dimensional stuff, you get just the Schur polynomial. And one more thing you can do is you can take the union of dual cogent with the corresponding permutation and intersect it with your cellular decomposition and take the cells lying in these spaces. And this will give you a Lascoux polynomial. And here's the combinatorial picture. I just want to.
Sorry, once again.
Yeah.
Take the cogent faces, the dual cogent faces you were having before, and you combine them with the self-decomposition of the one.
Yeah, that's right. That's right.
And this gives you exactly the Lascoux.
Exactly. Yeah. So, okay. So, okay. So here's the idea of you need to these Gelfand-Zetlin patterns, you need to add some bells and whistles, and some edges, some vertices are fixed. So these are called enhancements of a pattern, and an enhanced pattern defines me a cell and apparently a monomial. As I said, some cells define zero monomials. There is a nice combinatorial condition that if you have triangle with the same entry in all these vertices and there is no edge going northeast, then this is an inefficient pattern, so it corresponds to 0. And this happens pretty rarely. So here are the main results these enhanced Gelfand-Zetlin patterns really correspond to cells of a cellular decomposition. That my Lascoux polynomial is obtained, as you said, by taking the sum of these monomials, with the corresponding power of beta over all efficient patterns, such that the cell is in my union of faces. And as a corollary, if you take the whole cellular decomposition, you get the dual Grothendieck polynomial. So, the stable Grothendieck polynomial. So let me show you some pictures. Well, here's the cellular decomposition for GZ320, and the pink ones, the purple ones are inefficient. So there are only 2 of them. And And yeah, so you can kind of cut this into, sometimes you get some smaller Gelfand Zetlins or, so there are three-dimensional pieces in this case. Okay, and here's how you get Lascoux polynomials. So say the union of two green faces gives you Lascoux polynomial. Well, here I use this superscript beta. It doesn't matter. But so the purple face behind is shown on the left. So with monomials, you just take the sum over these. So yeah, and one last thing I'd like to say is that right now I'm trying to generalize this to subtype C. So they're all ingredients are there, so to say. There is an analog of our theorem with Kiritchenko and Timorin by Naoki Fujita, and there are analogs of Lascoux polynomials defined by Eric Marberg and Travis Grimshaw, and and I'm trying now to relate to. Okay, that's all I wanted to say. Thank you.
Thank you for your talk. Questions?
Well, I want to give comments. First of all, I don't understand. It was some maybe misprint because pi isobaric square of isobaric polynomial operators in constant is not p square not equal to p, but it is equal to p multiplied by beta. Because this is not exactly, it is some projector, but not p square is equal to p, possible. And I want to have comments about beta, because beta, I met Alain Lascoux, now almost 50 years ago, and he taught me what is Schubert polynomials, Grothendieck polynomials, and so on. And a bit later, maybe 40 years ago, I and Sergei Fomin, we understood that really all this theory, as in many cases, you have to replace in combinatorial story -1 by parameter beta. And in this case, Nakayama Murakami rules and many other rules, Grothendieck polynomials and so on, they contains -1 from geometrical reasons, but from algebraic reasons, you need just replace -1 everywhere by beta. And all known classical results can be, not all, but almost all results may be generalized to this setup. And we wrote maybe now, okay, about 35 years ago, a paper with Fomin about beta Grothendieck polynomials. And I want to say that Lascoux always consider K-theory, classical K-theory, when beta equal to -1. And at that moment, there are no interpretation of this theory with beta in theory as a generalized cohomology theory. But again, maybe 20 years ago, some person create analog of K-theory for full multiplicative formal groups. He introduced what is K-theory for this multiplicative group with beta. So till now, and also I want to take so in some sense, what Lascoux polynomials is defined here, it was what I call the K Grothendieck polynomials, and was introduced maybe 20 years ago. And this particular case of so-called what I called Grothendieck polynomials. Yes, and I also want to say about geometric interpretation of key polynomials or other polynomials in terms of Gelfand pattern, because this is also very famous region, very a lot of papers about this connection, and basically it related with the fact that Gelfand polytopes can be interpreted as a so-called flow polytopes. And the flow polytopes really defined in much more general situation. And for special polytopes, for example, Gelfand polytope corresponds to complete graph. But anyway, there is papers of Demazure, Morales, Escobar, and so on, which interpret these special Grothendieck polynomials corresponding to lambda, really here, as Grothendieck polynomials corresponding to corresponding flow polytope. Yes. Okay, I have a motto, maybe personally I want.
Okay, well, thanks a lot for a comment.
Yeah, thank you very much.
Unfortunately, there are no more time for questions because staff are waiting us for a group photo in the front of this building.